Hello, everyone. I'm Charlie Sharpless, the Assistant Director for Research at the Yenan Center for Energy and the Environment at Princeton University. I'm pleased to welcome you to our summer seminar series, New Light, Rising Stars in Energy and the Environment. Here we feature weekly talks by early career researchers working with faculty at the Yenan Center, where our mission is to develop practical solutions for a sustainable energy future. Reflecting the transdisciplinary nature of this mission, this series spotlights the next generation of leaders from a diverse array of fields across engineering, energy systems, material science, social sciences, public policy, and more. We're excited to host these outstanding scholars and bring their research to you through this series. Before continuing, I'd like to note that if you have questions at any point in the talk, feel free to type them into the Q&A box. At the end, we'll also have the raise hand feature enabled, and you can ask questions through that too, and we'll address as many questions as we can in the available time, starting with ones that we get through the Q&A box as the talk is proceeding. Today, our speaker is Dr. Yenan Chen. Dr. Chen earned his bachelor's and doctorate degrees in electrical engineering from Zhejiang University in Hangzhou, China. For the past few years, he's been a postdoctoral research associate working with Dr. Minji Chen, an assistant professor of electrical and computer engineering here at Princeton. Work in Dr. Chen's group focuses on developing novel, high-efficiency electronics for power management in a variety of applications, including distributed energy resource integration, electric vehicle operation and charging, data centers, and portable devices, among many others. Please join me in welcoming Dr. Minji Chen, who will introduce today's talk.
Yeah, thanks, Charlie. You pretty much have introduced Yenan. I just want to add a few words. So Yenan has been working in my lab for about 3 years, and he has worked on multiple projects ranging from low power CPU voltage regulators to high power grid interface power electronics. He has won multiple awards, including Best Paper Award at Compal, Princeton Innovation Award, Best Presentation Award at APEC, and he's really a racing start in power electronics, in the field of power electronics, and we're very excited to hear what he has to say about how do we deliver energy to all kinds of future electronic systems, and how do we interface those electronic systems with the electric grid. All right, so without too much delay, let's welcome Dr. Yenan Chen for his talk.
Hello, everyone. Good morning, everyone. I'm Yenan Chen. I'm a postdoc of the Yenan Center and the Department of Electrical and Computer Engineering in Princeton University. I'm glad to present our research in the Yenan Center Summer Seminar. Today, I will introduce the new power electronics architecture and the topology for efficient energy delivery system. At first, I will give a brief introduction to the power electronics. So because we are the only power electronics research group in Princeton, so I guess some of you may not be familiar with power electronics. Power electronics is a technology that processes electrical power using semiconductor devices. Basically, we design all kinds of power electronics converters. The power electronics converters is the interface between the energy source and the load. And also power electronics exists in everywhere of our daily life. Here are some examples. I think the cell phone charger and the laptop adapter are the most familiar power electronics converters. They convert the AC power from the utility grid to the DC power. And if you have a rooftop solar panels, a solar inverter is needed to convert the DC power from the solar panels to the AC power and send the AC power to the utility grid. And also the electrical vehicles also need a DC to AC converter to drive the motor. The third example is the CPU power supply. On the motherboard, it's a DC to DC converter. It gets power from the high input voltage of the motherboard and provide a very low voltage to the CPU. The last case is the electric chain. The chain speed is controlled by the frequency of the motor voltage. This frequency is controlled by an AC to AC converter. So we can see there are 4 types of power electronics power conversions. So now let me introduce the basic knowledge of the power conversion. In power electronics, we use semiconductor switch to sample the energy. In this circuit, the position 1 means sampling the energy, and position 2 means no energy sampling. By continuously turning on and turning off the switch, the DC input energy becomes discrete energy pulses like this. The amount of the energy can be controlled by the sampling time. So this is the basic of the power electronics. And also, we also need the energy buffer to store the pulse energy and provide a smooth output. The energy buffer is inductors and the capacitors. The semiconductor switch are not like the mechanical switch. They are working at a very high frequency from hundreds of kilohertz to megahertz, and the energy buffer can be small. So I put a picture of the basic power converter on the right side. So we can see the switches, capacitors, and inductors. And the energy sampling switch is a semiconductor switch. Usually, we need two switches to perform the energy sampling like this. So there are 2 operation states. If S1 is on and S2 is off, the input energy is sampled. And when S1 is off and S2 is on, that means there's no energy sampling. So also, when the switch is on, it needs to carry the input current. And if a switch is off, it needs to block the voltage. So for semiconductor switches, there is a maximum voltage called breakdown voltage, which means this voltage will destroy the chip structure of a semiconductor switch. Higher breakdown voltage requires a thicker conducting channel of the switch. So therefore, the resistance of the channel will also be higher with higher breakdown voltage. So generally, this is a basic knowledge from semiconductor material is with the same chip die area, the semiconductor switch with lower breakdown voltage usually has better performance because the resistance will be smaller. So finally, I will introduce how to evaluate the performance of the power converter. Because of the power loss of the every components and the parasitic parameters, the output power of a power converter is always lower than the input power. So, and the power loss will be dissipated as heat. So the components temperature of the power converter will be very high during operation. And we use efficiency and power density to evaluate the performance. Efficiency is output power of input power. So efficiency is always below 100%. And our job is to improve the performance of the power converters. Then I will introduce 2 examples. The first example is multi-input, multi-output energy router for large-scale modular energy systems. And this is a schematic of the modern utility grid. So we can see there are power plants and large-scale solar power plants and the wind power plants. And also there are home load consumers with distributed solar and the EV charge stations. So in this structure, all the power plants, renewable energies, and the consumers are integrated by the utility grid, and all the power are transmitted by the grid. So as a power electronics researchers, what we see is there is a large amount of individual power converters in the utility grid. So these power converters are usually targeting for different working conditions, and so we cannot guarantee all of them are well designed with good performance. So these individual converters, like different cars with different performance, like a supercar, and some converters just like a scooter. And also, this structure is not smart. So the smart we mean is the energy can only be transmitted by the utility grid. If we want to charge the battery directly with the solar power need to be processed through multiple stages. The solar power need to be delivered to the utility grid first, then transfer back to the batteries. So this way, so in this path, there are too many power conversion stages, and the efficiency will be low. So we design a MIMO energy router structure. It's very similar to the network router. The network router communicates to the all network devices in a building and exchanges the information with the internet. And similarly, the energy router controls the power among multiple sources and loads for a system. And it also transmits the power to the utility grid. So one difference is if the source power and the load power in this system are balanced, there is no power coming from or sending to the grid. So that means the power of this system is self-balanced. And the MIMO energy router is very suitable for large-scale modular energy system like solar system, battery system, and the data center servers. So in solar systems, there are many solar panels connected in parallel and in series to provide high power, as similar as the battery system and the server system. If we use the traditional structure, we need a lot of individual converters. So as we know, these converters, the performance are different, and some converters' performance will be very poor. And the MIMO energy router is it's more like a high-speed chain, which has a better efficiency and power density, and has lower weight and lower cost. One obvious advantage of the MIMO energy router is we can directly regulate the power among multiple sources and multiple loads. For example, we can directly transfer the solar energy to the battery, and we can directly use the battery energy to power the charge station and data center without exchanging power with the utility grid. So there are fewer power conversion stages, and the efficiency will be higher in this MIMO energy router architecture. Then we further developed a reconfigurable multi-cell, multi-input, multi-output energy router architecture, because we find the MIMO energy router still need to interface our wide range of voltage and current. So as we know, it's very difficult and expensive to design the converter for a wide operation range. That means a wide operation range means the semiconductor switches used in this converter need to block both the maximum voltage and need to carry the maximum current. So the performance of this switch will be low, and the price of this switch will be very high. So we utilize many modular switching cells, with different kinds of series connection and the parallel connection. For high voltage, we stack the switching cells, and for high current, we put the switching cells in series. So in this reconfigurable structure, we can use low breakdown voltage device, while in an individual converter, the switch need to block both high voltage and high current. So with low breakdown voltage device, the performance of the converter will be better, and the overall system efficiency will be higher. And this is the basic structure of a single switching cell. So it has the 4 switch for the energy sampling, and also has the local energy buffer. The local energy buffer means there is no energy buffer between any 2 terminals. So we can save a lot of buffer components in this architecture, and the overall system will become more compact and more cheap. Here is a design example. Because we are using low breakdown voltage switches, so we can see actually these switches are, the package are very small, and the whole system is very small, and the power density is very high. So we design a converter MIMO energy router with maximum input and output ports up to 12 ports. So these 12 input and output ports can be reconfigured as the different voltage from 9 volt to 288 volt, and also for a wide range of current. And we also test the efficiency. So this prototype can achieve a very high efficiency in a wide operation range. So this is the main advantage of this MIMO energy router design. And so by now we already introduced the advantage of the MIMO energy router, but actually there are also design challenges to the MIMO power management. So one challenge is the power flow of all the energy source and the load are coupled by this transformer. For example, if the output power of the solar changes, the power distribution of other source and load will also change if no further control is applied. So the MIMO energy router need very accurate modeling for the control, and also very accurate power measurement and accurate energy sampling. So that requires the semiconductor switch to has the very good performance. And by now there are many power flow control methods proposed for the MIMO energy router. Another application of the MIMO energy router is the multifunction battery balancer. So the circuit of this multifunction battery balancer is similar to the MIMO energy router. But so now the battery are connected in series, and the battery balancer can balance the voltage of each single battery by exchanging the charge of with the high voltage battery and the low voltage battery. And furthermore, this balancer can do the online impedance analysis by injecting the AC current ripple to individual battery. So the impedance analysis of the battery can focus the potential battery failure. So this can improve the system stability and the reliability. And the third function is self-heating of battery. So we know when the temperature is cold, probably your cell phone cannot be turned on. And with this self-heating function, by also injecting the AC current to the battery temperature can be increased, and the battery life will be extended. Also, this will improve the battery performance. And next, I will introduce an example of the ultra high current CPU voltage regulator. So the CPU and the other microprocessors on the motherboard, their supply voltage is very low. It's about 1 volt, and the power is from the utility grid, from the high voltage AC, and the power is converted by the server power supply to multiple different kinds of DC voltage levels. And on the motherboard, the standard input voltage is usually 48 volt for modern data center server racks. So I put an picture of the motherboard of NVIDIA Tesla high performance microprocessors. So this single CPU, the operation voltage is very low, it's around 1 volt, but it consumes a large amount of current. So now the maximum current is 400 amp, but in the future, with the high demand of computing and communication, the performance of the CPU will be improved, and as well as the power consumption. So in the future, the single CPU power current consumption will be up to 1000 amps. So this brings the challenges to the 48 volt to 1 volt converter on the motherboard. So first is the high voltage conversion ratio. You need to convert the high voltage 48 volt to 1 volt or below 1 volt, like 0.7 volt. And also, at the same time, you need to provide a very high current at the output, and while still maintain the high efficiency above 95%. As we know, so actually the components are nonlinear. So every components like the PCB, the printed circuit board, the copper trace, they all have resistance. So with such high current, 1000 amp, the conduction loss of the resistance will be very high. And this loss will also become the heat. So the thermal management of the CPU power supply is also very important. And also, we can see in this board, these yellow rectangles are the converters, the 48 volt to 1 volt converters. They already occupy a large PCB area. So if we increase the power, for sure the PCB area of the power converter will also increase. But this is not wanted by the CPU designers. So our job, one of our job is to improve the power density to reduce or keep the same PCB area, but improve the output power. And the last challenge is high bandwidth. High bandwidth means the CPU voltage regulator can respond to the load step change quickly, because the modern CPU, the switching frequency, the operation frequency is gigahertz. So our converter also need to be able to respond to such a fast response. And so for the 48 volt to 1 volt design, the most straightforward way is we directly use this energy sampling and energy buffer circuit to convert the power from 48 volt to 1 volt. We can only adjust the sampling time, so the average output voltage will be 1 volt. with a very tiny sampling time. But actually, nobody will do this because in this circuit, the switch, most two switches need to block the high input voltage, like for the 8-volt, but also need to carry the high output current. So if our system output current is 400 amp, so each switch need to carry 400 amp. And let's see this curve. So similarly, with higher breakdown voltage, the on resistance of the switch will be high, and with such high current, the conduction loss of the switch will be also high. So this converter, the performance is really bad. And another solution is we cascade multiple stages to decouple the voltage and current rating. For example, the first stage, we convert 48 volt to half of the input voltage to 24 volt. So the voltage rating of the first stage is still the 48 volt, but the current rating is only twice of the input current. And for second stage, we also do a conversion with low voltage conversion rating. For example, from 24 volt to 12 volt, this only the conversion ratio is half. And for the following stage, we also do the similar conversion. So in this way, the voltage rating and the current rating can be decoupled, and the switch do not need to block the high current and carry block the high voltage and carry the high current. But the disadvantage is there are too many components and too many power conversion stages in series, and also the power need to be processed through all the stages. So that means the overall power loss will be very high. So actually, this is also, so this solution is also not a good solution for the 8 volt to 1 volt conversion. And so the third solution is, how about we connect all the power converters in parallel? So in this way, the input is connected in parallel, and the output is also connected in parallel. And the voltage rating is still the input voltage, but the current rating can be reduced to the 25%. So this solution can only reduce the current rating. So, and one more step is we can also put the input, connect the input in series and connect the output in parallel. So in this configuration, the input voltage rating is divided by 4, and the output voltage rating is also divided by 4. So this one looks like it's the perfect, it's the better solution for high voltage input and high output current power conversion. But the question is how to do this. So we use this circuit. So this circuit is very similar to the basic energy sampling and energy buffer circuit I showed in the previous slides. So, but I insert additional capacitor between these two sampling switch on the top three switching cells. So with these additional capacitors, the voltage can be, the DC voltage can be blocked, and the input of these 4 stages can be connected in series. And it's worth to add in more capacitors to reduce the switching voltage rating, because with lower switching voltage rating, the performance of the switch will be much better, and they are also working in the better operation conditions, and the overall efficiency will be higher. And this is our final design for the 8 volt to 1 volt high current CPU voltage regulator. So at first we put a pre-conversion stage. So this stage converts the 48 volt input to a 24 volt intermediate bus. And the second stage is the circuit I mentioned in the previous slide with the series input and output, parallel output configurations. So the input of the second stage is 24 volt to 1 volt. So the voltage conversion ratio is 24 volt to 24 to 1, but the equivalent input voltage of each switching is 6. So we can use the low breakdown voltage switches, and the switching voltage is also lower. So the switching performance can be improved, and the overall system efficiency also improved. And also we use many switching cells, like totally 16 cells to support the high output current. And this is our test bench and the prototype. This is the prototype of the 48 volt to 1 volt CPU voltage regulator. So you can see there are several capacitors and switches on top of the circuit board. Then this is the old test system. We use this is the data collection system, and we collect the input power and output power, and to calculate the efficiency. This is the input source provided 48 volt voltage, and this is the converter and the cooling fan, and we also use 2 high current load to support the high output current, to consume the high output current. And we measure the efficiency, system efficiency. The efficiency is calculated by output power over input power, and we can see we measure 3 different output voltage from 0.8 volt to 1.2 volt. So these three voltage are a very typical supply voltage level for microprocessors like CPU and GPUs. So the peak efficiency with 1 volt output is about 95%. And we also did some search, and we believe that this is the best peak efficiency both in the industry and the academia. And this is the thermal image of this converter, of our converter. So we can see the ambient temperature is around 30 degrees, but due to the power loss at the full load, the component is very hot and temperature is around 80 degrees C. And we also test the dynamic response with the load step change. So the load current is stepped up from 50 amp to 350 amp, and then stack back to 50 amp. And the output voltage is regulated and remain stable. And the previous experiment efficiency result and the temperature result is measured with the cooling fan. The cooling fan is a very typical cooling solution for computing server. And if we want to further push the output current, we need better cooling solution. So we use the immersion cooling. Immersion cooling is a better solution for high performance server. So we put the server motherboard into the cooling liquid. It's like it's like oil. And this is just an example of the immersion cooling for the server. And this is the real picture of our experiment setup with the liquid cooling. And with the liquid cooling, the output current, the maximum output current can reach 600 amps, 40 amp at 1 volt. And with, as we remember, with the fan cooling, the output current, maximum output current is 400 amp, 50 amp. So the maximum output current is improved by 200 amps. So let me show a video of the liquid cooling. So this is the multimeter. We use multimeter to measure the input power and output power. This is a load. They are consuming 600 amp, 640 amp. But we can. And also we did a research and did a search and compare the performance of our converter to the other converters, both from the academia and the industry. So this work is targeting extreme efficiency, and our peak efficiency is higher than 95%. So this is the position of this work. And our full load efficiency is also high and with a relatively high power density. And our group has another topology, the targeting for extreme power density. So this is the picture of the second topology, which targets the extreme power density. So we can see this topology, the peak efficiency is around 91%, but the power density, the current density is around 1 amp per square millimeter. And the power density is 1,000 watts per cubic inch. So these are also the highest record in both academia and industry. So so we can announce Princeton University invented 2 CPU voltage regulator, which has one has best peak efficiency and then one has the best power density. So to conclude, in today's seminar, I gave the examples of 2 emerging energy delivery systems. So one is the MIMO energy router. It has a sophisticated power flow with multiple energy source and multiple loads. And the second one is the 48 volt CPU voltage regulator. It has the extreme voltage conversion ratio from 48 volt to 1 volt. And also it has very high current stress up to 640 amps. So the key idea to improve the efficiency and performance of this energy system is to reduce the voltage and current rating of semiconductor switches by advanced circuit architectures and topology. So for the MIMO energy router, we use the reconfigurable multi-cell architecture. And for the 48 volt CPU voltage regulator, we use the capacitor-based series input parallel output architecture to decouple the voltage and the current rating. And this concept can be applied to many other power electronics converters to improve the system efficiency and power density. And this is my presentation, and I would like to thank to our principal investigator, Professor Chen, and all the members of the Princeton Power Electronics Research Group. And also these 2 projects are sponsored by Annenlinger Center, the Institute and the PSME company. So thanks for watching my presentation, and please feel free to ask questions.
Yeah, thank you very much for that excellent presentation. I feel like I understood all of that, even though I took one circuits course in college many years ago. So I really appreciate the clarity of what you presented there. We have a couple of questions from some audience members. I had one quick question to start though, which was in your multi-cell MIMO, it seemed so small, and you showed a 56 amp maximum output and 288 volt maximum output, which is 16 kilowatts. Is that really the maximum output? Is that the maximum power output for that guy?
Oh, so actually, the maximum output, the maximum voltage and maximum current, they cannot be reached by the same time. So we can look at this curve. The red curve is the power curve. So that means the maximum output current, maximum operation current of this converter. So for some applications, the voltage is high, but with the constant power, the current is low. And for the other applications, the current is high and the voltage is low.
Gotcha.
So if we, right, so our the multi-cell MIMO energy router is targeting the applications that has a wide operation range. So we can use multiple cells to support the high voltage and support the low current.
Gotcha. So is that red line a constant power line?
Right.
Gotcha. Let's see, the questions that we have 3 questions. I'm going to take them in the order that they've shown up here. Early on, an anonymous attendee asked, can you comment on the increased control complexity of the MIMO energy router compared to the traditional method? And I think this was asked when you were comparing the traditional distribution off the grid, versus the centralized management through the MIMO. And I guess the question about the increased control complexity for me speaks to the types of processors that need to be working to do the management relative to all of the converters working independently on the grid.
Yeah, so in the traditional architecture, actually, for the power converters, there is no communication between different power converters. So they are all doing the single input, single output operation. So they have, most of them have very simple control target. For example, to regulate the voltage of the load or maximize the solar power generation. So the control in the traditional architecture is relatively simpler because there is no interaction between different power converters. But in this MIMO energy router, so because we use the transformer to couple all the converters together, so the power flow is coupled. That means any disturbance on one energy source or one load will change the power flow. So the power flow is more complicated in the MIMO energy router, but we still have a control method to stably and precisely regulate the voltage and regulate the power in the MIMO energy router. And these control are all implemented by software. So actually, by the microcontroller. So the hardware setup of the control is still the same, but the software will be complicated than the traditional control of in the traditional architecture.
So Charlie, I guess I can add something to this question. It's a very good question. So one philosophy in power electronics is we simplify everything in power, because if we compare the cost or volume or size or technical challenge, dealing with megawatts of power is much more challenging than dealing with microwatts or watts of microprocessors. So one of the design philosophy is to simplify the power stage as much as possible and push all the challenge to low power, dealing with everything at low power, dealing with everything with software and control. So that's sort of one of the major design methodology that we are taking in our group is we think, how can we make power converters smallest, cheapest, lowest cost, most efficient, highest performance? Well, it's more complicated control. It's very difficult to control, very challenging, a lot of very interesting questions in terms of control, but that's something we can solve with the modern computers and microprocessors and algorithms, and even machine learning and AI. So some of other group members in our team, we are working on how do we use machine learning to deal with these sophisticated control problems. So a lot of opportunities there as well.
Thank you. Let's see, Jayobek had a question. Thank you for the good presentation. For the MIMO energy router, 2 questions. One is, how much voltage difference or power difference can the router handle? Is there a voltage or power range constraint among the end units to loads? And then the second part of the question is, in the case of several loads, if they're far away from each other, how do you manage the distance, or how much does the distance need to be managed between the router and each individual load?
So excuse me, Charlie, can you repeat the first question again?
Sure. The first question is, how much voltage difference or power difference can the router handle? So is there a voltage or power range constraint among the loads? So I guess how different could the various different loads be in terms of the voltage and power required? So the battery storage versus the solar farm versus the charge station, can those be wildly different in their energy requirements? So do they need to be within a certain range?
I think they can. The operation range can be very wide, because so first is actually when we talk about the MIMO energy router, we actually are routing the power flow through this transformer. And also one basic knowledge is transformer is not storing energy. So the transformer can be small and can handle very high power. So I think the power range of the multiple different energy source and load can be wide. And the power, so the power difference and the voltage difference is only related to the switching side, the semiconductor switch design. And with higher power, that means for our multi-cell architecture, we need more cells connect in series and all connect in parallel for a very high power port. And for low power port, we need fewer switching cells. So I think in the end, this becomes the optimization design for this system. So which is the optimal operation point of power and voltage for each port. But by now we haven't done much analysis about this, but I think this architecture can support a very wide operation power and wide operation voltage.
Gotcha. And then the second part of the question was, in the case of several loads, do you have a sense of how physically distant they can be from each other to still function? Or is it?
Yeah, that's really a good question. So ideally, we hope we can integrate all the energy source and the loads with one energy router, like the primary energy router. But due to their physical location and the different distance, if we integrate all of them in one energy router, that means we need a very long distance cable. And also this cable are directly connected to the transformer. So that will make the system modeling very complicated. So in our architecture, actually, we put a primary energy router and also several energy router with smaller power rating, but closer to the energy source and loss to improve the performance and to solve this solve issue caused by the different physical location and distance.
Gotcha. A few more questions here. Jack Robinson asks, when do you expect either of these to be commercially available, be the 48 volt to 1 volt converter or the multi-cell MIMO system? Are they close to having someone actually put them into production?
So for the first example, I think there are already several demonstration projects, both in the academia and industry. But I think this architecture is not, maybe it's not suitable for a simple commercial product. I think it's more suitable for as a type of a project or a program for the specific operation voltage and needs a specific design for the first example. And for the second example of the CPU voltage regulator, this project is collaborated with a company, and I think this will be very quickly become the commercial product. Gotcha. Because the company is very interested in this architecture.
Excuse my dog. I'm going to ask this next question. Kind of loud to get over my dog. So Jinyuan asks, do you have any considerations about EMI aspects for the proposed converter? And I have to admit, I don't know what EMI stands for, but I assume you do. So for the 48 volt to 1 volt converter, are there EMI aspects about that you have that are important to consider?
The EMI, I think, so basically the EMI is the same as the traditional 48 volt to 1 volt converter. And I think our product has better EMI performance because our converter are switching at lower voltage. So one EMI source is the dV/dt delta V over delta T during the switching transitions. So with higher dV/dt, the EMI problem is worse. But in our converter, we are switching at lower voltage. So I think our EMI will be better.
Oh, so this is electromagnetic interference is what EMI is. Yeah, I got you. Cool. And then we have one more question here. Sepe Safari asks, what are the future trends of this technology and where do we go from here? Which seems a good closing out question.
Okay, so I think for both two examples and also for all the power electronics converters, and so we are all pushing the power, pushing higher power with higher efficiency and higher power density. This is our goal, and this is the goal of every power electronic researchers. So I think this technology has very wide application in the future, not only in this energy, minimal energy router and high current CPU voltage regulator, it can be applied to the many other power supplies such as solar inverter and like battery charger, EV charger. So because this concept is common in power electronics, just using the lower breakdown voltage can improve the system performance. So I think the challenge and difficult is how do you invent the new circuit, new topology to utilize the new low breakdown voltage instead of a high breakdown voltage. And so where do we want to go is so we always want to improve the efficiency and the power density of power converters. Even we cannot reach 100% efficiency, but always the efficiency higher is the better. And actually, in some applications, the power electronics converter, the efficiency of the power electronics already is higher than 99%. So, but we still want to further improve the efficiency to save the cost and to save the energy and also it also helpful to reduce the carbon emission. So that's what we want to do.
So I guess as you were answering that, it made me think of one more question, which is, what you're doing is very clever designing of the circuitry to maximize the efficiency. What kinds of trends are you seeing or expecting in development of new materials that can help you make better circuits?
Okay, yeah. So for power electronics, so one research area is the semiconductor device. This is related to the semiconductor materials. And so traditionally we are using silicon material semiconductor devices. And now there are also very new, many new material, new semiconductor devices like silicon carbide material and gallium nitride carbide. So this material has better performance than the silicon materials. And this with this new material, so if we go to this curve. So with new material, we can achieve better system performance with the better performance of the switch. And so the efficiency and the power density of these converters will be even higher with the new device, new material.
Gotcha.
Charlie, regarding research vision, I probably can add something. Yenan sort of emphasized a lot on efficiency, but he didn't mention that power electronics at the same time is also a enabling technology for many, many applications. For example, if we want to build aircrafts that are powered by battery, batteries are super important. Of course, we want to make batteries light enough, and power electronics is super important as well, because if you make power electronics small enough, efficient enough, if power electronics not small enough or not efficient enough, it's not impossible, because you're just wasting your battery, wasting your energy on the flight. And every weight, every efficiency, every 1%, even if it's 1.1%, 1% of efficiency improvement means 1% more mileage or 1% less batteries. And at some threshold, the efficiency is not really a target, but really a yes or no. If you pass this efficiency target, your system becomes possible. If you didn't pass this efficiency target, your system is just not possible. So it's really a 1 and 0 difference instead of like 1% efficiency difference in some case, because everything needs power electronics and it's at the core of everything.
That makes sense. Thank you. Well, it looks like we are out of time. I want to thank you, Yenan, thank you again for that presentation and the engaging question and answer session. I also want to thank the Endlinger Center staff who are working hard behind the scenes to deliver this seminar series. And finally, I'd like to thank all of you for attending today. Next week's webinar will be at 11 a.m. on Thursday, July 15th, when Dr. Sean Zhang will discuss his research to develop low energy approaches to water purification and desalination. You can find a link to the speaker seminar series in the chat box. And the registration links are there as well. We look forward to seeing you at future talks. And in the meantime, stay safe and healthy and have a great week.